Hey there, everybody. What's up? Welcome back to the channel. We are going to be looking at organic chemistry, reactions of organic chemistry 2 is what your channel said for the night. You might be looking at this and saying, well, wait a minute, Tyler, or reactions of organic chemistry 2? I don't remember doing reactions of organic chemistry 1, and that is a good observation. We're going to be doing reactions of organic chemistry 1 later on this evening. And Zinga's going to come on in an hour. She's going to hit us up with some great knowledge bombs, and then we're going to come back for more organic chemistry. And actually, I wanted to point that out because these are not two sessions where one feeds into the other. They are two freestanding sessions that happen to be called Organic Chemistry 1 and 2. So tonight, right now, in fact, we're going to be looking at alcohols, ketones, and aldehydes. Later on, we're going to be doing some substitution reactions, some reaction conditions stuff. Having said that, we've got a ton of stuff to do, so let's dig in. What are we going to do here? 5 different things. We're going to look at naming and property of alcohols, and then we're going to look at reactions of alcohols. We're going to look at the properties and naming of aldehydes and ketones, and then we're going to look at reactions involving aldehydes and ketones. One of the great cross bridges of these topics is enolates, and we'll talk more about enolates as well, ending the day with a series of many different reactions, which you guys will hopefully recognize are not so different after all. Yay! Instead of tons of memorization, what we're going to do is approach this all from a bit of a critical thinking standpoint. Starting with the nomenclature and properties of alcohols, let's begin with maybe the most obvious question. Here, we're going to look at naming. How do we designate alcohol when it is the highest priority functional group? OL, yeah. What about when it's not the highest priority functional group? Hydroxy, yeah. And then how do we recognize what the highest priority functional group is at the end of the day? Yes. A chemist will say the oxidation state, the most highly oxidized carbon on the molecule. Yes, that's technically accurate and awesome to know. How do we actually recognize which carbon is the most oxidized in a general context? Or like the trick for the MCAT? Yeah, the most bonds to oxygen, right? The one that has the most bonds to oxygen is going to be the most oxidized carbon. Now, there are technicalities and exceptions, and you could say, well, wait a minute, Tyler, I've seen situations where that's not necessarily the case, and that's all very true. But as a trick for most MCAT questions, and for today, oxidation equals bonds to oxygen. So here we have a alcohol with several different properties. What we're going to actually do here is take a look at a few different examples. Now, I am not going to ask you guys to name these compounds. That's dumb, because as Eli just pointed out in the learning and memory lesson, this is not a test where you're going to be naming things straight out. You're going to be picking the one right answer out of 4 choices. So let me ask you guys, looking at this molecule, what are some features of it that you want to recognize that the right answer must have? It's got an alcohol, so and it's going to have 4 carbons. It's going to end in OL. Yeah, exactly. Right? We know that the answer here has to have but in the root because it's got 4 carbons. It's got to end in OL because the highest priority functional group is an alcohol group. In fact, the only functional group. And finally, what carbon is that guy going to be on, ladies and gentlemen? Yeah, the 2 carbon. Now, if you identified those key properties, guaranteed, 100% of the time, you get the question right. 2-butanol, kind of a warm-up here. Take a look at this guy and tell me, ooh, what's the highest, actually tell me the suffix associated with the highest priority functional group here, since this is spotting the right name kind of a thing. Yeah, you'd be looking for the one that says oic acid. Nice. Now, there's a hydroxyl group. So we're going to see a hydroxy prefix, and to what carbon would that guy be attached? Carbon number the 3rd, right? Because we give the lowest number to the highest priority functional group. That's what we're going to see here. Higher priority functional group gets the lower number, and that means that the hydroxyl group is bound to the third carbon. 1, 2, 3. There we are. Sweet. Take a look at this guy, right? One thing that we need to know for test day is the positions. What position are these two substituents relative to each other? So the way I always remember this, orthometapara, you've probably been taught orthometapara, that corresponds to the actual relative substituent locations. Ortho is first. If they're right next to each other, that's where ortho comes from. You might remember meta is in the middle. Meta is between ortho and para. These guys are meta to each other. Now, I noticed we were a lot weaker in the chat on that result. That's good. Learn from that now. Because I guarantee on test day, if you recognize that these are meta to each other, that alone is going to get you down to at least a 50-50. This is a phenol molecule. It has a chlorine group meta. That is going to be enough to spot the right answer overall. Sweet. And then we get into, oh my goodness gracious. Oh my goodness gracious. First off, gang, what's going to be different about the root of this given that I have this double bond? So it's going to have an ene in there, and then Anna, Rachel, Christopher, you've got the other stuff here. This is a diol as well. If you look for those features, probably that's going to be enough. Probably that's going to be enough to answer the question. You have the ene, you have the diol, maybe you also need the number of carbons in the root, but those things taken together are probably going to be enough to get you the right answer on a process of elimination. Cool. Now, let's look at physical properties of alcohols. Alcohols generally have a higher boiling point than other compounds of a similar weight. Why? Why would alcohols generally have great mnemonic, Eli? Yeah, H bonding, right? It all boils down to good old Coulomb and his law. Opposite charges attract. What we see here is oxygen, highly electronegative. That's going to make a polarized bond, and those polarized bonds are going to interact with each other in a process we like to call H bonding. There it is. So if we wanted to look at how this translates into chemical and physical properties, I'm noticing the one on the right definitely going to have a very, very high boiling point compared to the other two. Why? Why would we see higher and higher boiling points as we go further and further over to the right? Just as easy as that. More OLs. Yeah. Good. Keep going to the right. Right? Now notice, propane, right? If you are familiar with the television show King of the Hill, you know Hank Hill sells propane and propane accessories. Propane is a gas at room temperature. One way to think about that is it has already boiled at room temperature. Notice that we've not really changed the weight that much. We've added a whole functional group, sure, but we go up a few AMUs, and the boiling point goes way, way up. The boiling point of propanol is like 97 degrees Celsius. Much, much higher. And of course, adding three hydroxyl groups, we see that trend only continues. Hannah, alcohol doesn't freeze in the freezer for a related reason. That is that it doesn't stack as well as water, so it's hard to um, get it into that solid state. And that's a great point Hannah's bringing up. Actually, when it comes to boiling point, the trends are very easy. It's all about intermolecular forces. When it comes to freezing points, there's alternative explanations and opposing trends. We've got stackability versus intermolecular forces versus molecular size. Which one do you think the MCAT is more likely to ask you about? The one where there's an objective criterion based on a trend, or the one where we have lots of different competing factors? Probably about boiling points. Almost always, unless they give you a data table, They're going to ask you about boiling points because, as with most things OChem, they are not asking you to memorize a bunch of stuff. They're asking you to apply critical thinking trends. Nice stuff here, right? Now, alcohol protons are also weakly acidic. That is, they come off, not very likely, not very much going to come off. However, again, we're going to see that as we go further toward the right, it is more and more likely that I'm going to pop that proton off. Question for you guys, why? What do the molecules have on the right that would make them more acidic, make it more likely that we're going to be pulling that proton off? Good, good, good. Far, far right, I see resonance, right? When I pop off that proton, I'm going to be left with a negative charge, and if I can stabilize that negative charge, that's going to help us out. Now, Mary's got a great point here. Stability in general, if we take a look at the second to the right there, that's not necessarily an opportunity for resonance. However, what we are going to see is that fluorine is highly electronegative. So again, if I pop that proton off, and I have a negative charge, we're going to be drawing that negative charge density out across the molecule, spreading it around, and stabilizing the conjugate base. What do we call this effect? And I see one of you guys has it in the chat so far. This is not resonance, but it is another way to spread negative charge around a molecule. This is the inductive effect. Yeah, so what we see is that molecules that have inductivity or resonance, that helps with stability. And if you think that's the only time we're going to see this trend, well, I hope you were paying attention because it's coming back again and again. Again, we see that resonance, inductive effect, help us spread around negative charge, make things more stable, make us more likely to lose that proton, make it more acidic, all actually synonyms of each other. Beautiful. Nice. Notice even this molecule on the far right, pKa at 10, still not very acidic. Now, throughout this lesson, I want to point out, gang, we're going to have a few questions for you guys. This is such a jam-packed lesson. There's just no time for us to do these together. But we included them as homework, and we peppered them throughout the lesson so that you would very clearly see the skill that each question corresponds to, rather than kind of putting them all at the end like your normal channel homework assignments. This first question definitely has to do with alcohols. You can see that each of these ends in that alcohol suffix. And again, we're going to be continuing this trend throughout. We'll see questions scattered throughout here. Answers will be in the recaps at the end. Again, kind of ties into Eli's discussion from the first hour about using information shortly after you learn it, applying it overall. Okay, let's take a look at our second learning goal. We talked about nomenclature and properties of alcohols. Now, let's take a look at reactions of alcohols. I want to start out with, I see an actual alcohol here in the middle and lots of reactions going on around him. Notice if I react him with PCC, I get an aldehyde. What kind of a reaction are we looking at right here? Maybe this is a principle that we just talked about in a brand new application. Exactly. This is oxidation. My experience with organic chemistry is that most students, myself included, learned it as a giant pile of facts. What the MCAT's going to do is it's going to look for a few underlying ideas and see if we can't build on them. In fact, going the other way, you might be saying, what's going on there? What we're doing is we're turning alcohol into an awesome leaving group to make a highly reactive electrophile. Now, let me ask you this. Why is alcohol itself a terrible leaving group? Ooh, I like it. Again, ties back to Eli's first lesson about using dirty language to help you remember things, right? When we pop off OH, we get OH minus. What do you guys know about the stability of OH minus? That's a strong base. It's not stable. It's a terrible leaving group for that reason, right? If we kick it off, Joseph's right, it's probably just going to reattack and bind back on. So what we're seeing here is a reaction involving oxidation. We're seeing a reaction where we're turning a bad leaving group into a good leaving group. We will talk about this reaction a little bit later on as well. But these are all tied back to fundamental ideas: oxidation, tosylation, alcohol acting as a nucleophile. These are ideas that we're going to be building in the next learning group, starting with oxidation of alcohols, right? We take a look at a primary alcohol, and we can oxidize it to an aldehyde. Now, let me ask you guys, we have to be very careful with our choice of reagent here, because what is the danger whenever we're oxidizing primary alcohols? If I want to make an aldehyde, what might accidentally happen instead if I choose the wrong reagent? Right. Yeah, and again, you can think about a carboxylic acid. Now my carbon's got 3 bonds to oxygen, so we could actually oxidize it too far. We see that using the special reagent PCC, pyridinium chlorochromate, that's going to stop us at the desired result, right? Secondary alcohols, well, when I oxidize a secondary alcohol, think about it. My secondary alcohol, I know this is right on screen, so try not to cheat here. But a secondary alcohol is an alcohol where the carbon is bound to two flanking carbons. If I were to do the same thing, if I were to oxidize that alcohol and now have a carbon with a double bond to oxygen flanked on both sides by carbons, what functional group do I get then? Carbonyl flanked by carbons gives me a ketone. So don't let the structure of this slide trick you into thinking that these are so very different reactions, right? Both of them involve oxidizing something, an alcohol that is, to a carbonyl group, whether I have 1 carbon flanking it or 2 carbons flanking that carbonyl. That's going to be the end result. Cool. Now, what if I wanted to make a carboxylic acid? Why, then I would do the same thing. I would oxidize a primary alcohol. I would just oxidize it too far, and that would bring me to the end desired result. By the way, PCC, decent oxidizing agent. If we look here, dichromate and also chromate, these are very, very strong oxidizing reagents. So you should know that, Hannah. But I'm going to recommend you don't memorize these because you can recognize them at a glance as very strong oxidants. How? They got lots of oxygens. They got lots. Now, is your chemistry teacher going to be happy to hear you using that mnemonic? Probably not, right? But I am not your chemistry teacher. The MCAT has never met your chemistry teacher. So let's use every trick that we can throw at this test, right? PCC, where's the oxygen, buddy? That's how I can recognize PCC as not as strong an oxidant, and PCC will stop at 1 oxidation event. By contrast, chromate, lots of oxygens, he's going to oxidize me all the way. Same thing with dichromate in the second reaction. Good stuff. Cool. Now, we said that alcohol rather, is not a very good leaving group. So I might want to attack it with a nucleophile. And this is a reasonable thing to think, right? It's not a very reactive electrophile, but it is an electrophile nonetheless. Why would this carbon be susceptible to nucleophilic attack? What about it is attractive in a literal and metaphorical sense to a nucleophile? Sure. Yeah. So again, we talked already about oxygen being electronegative. What that means in this context is that oxygen is going to pull electron density away from carbon, making it attractive to a nucleophile, although oxygen is, the alcohol that is a terrible leaving group. So actually, if you guys aren't looking, if you're looking at away for a second, look at the screen for one moment. We've got the cutest little animation here. That nucleophile is going to try to attack, and just, nothing happened. Sorry, guy. Thanks for playing. Try again. You guys want to see it again? I did this like 20 times when I was getting ready for this lesson. Nope. All right, we'll do one more time here. Sorry. All right. Sorry, guys. Yeah. So this is not a very good reaction, right? We're not able to bump off that hydroxyl group because it's a bad leaving group. Literally true, actually, Eli. What we can do instead is we can replace that alcohol with a really good leaving group. It's a poor leaving group. So we're going to react it with a mesylate or tosylate anion to make it into a better leaving group. Now, if those sound like big fancy words, you're right. It's not terribly important that you recognize these compounds. What is important is that you recognize if I were to take this, for example, methane sulfonyl chloride, and I were to swap it out on my reactant, how could I recognize this guy as a much better leaving group? What about this guy makes him so much more stable after he gets kicked off? Sure, it's a sulfate, Lydia, exactly, and therefore, Joseph, it can destabilize that negative charge through resonance. And again, we're seeing ideas repeat themselves. I kick him off. That's a great leaving group, mesylate. Similarly, take a look at tosylate here. Tosylate is one of my favorites, man. Tosylate has tons and tons of resonance. And if I swap out my hydroxyl group for that tosylate group, then I have all of a sudden an excellent electrophile with a wonderful leaving group. This guy is a great leaving group. And again, if you wanted to kind of conceptualize this, basically I'm swapping out that hydrogen for all of this, or for all of this. It looks so different, right? It looks like such a modification. But all we've really done is replaced a bad leaving group with a good leaving group. Cool. By making it a bit bigger and fluffier. Now, let's bridge the gap between alcohols and aldehydes and ketones next. I've got an aldehyde up here on screen, and I want to kind of preface something we're going to talk about in a little bit. That is, an aldehyde is both electrophile and nucleophile. Where will I find a very good electrophilic group on an aldehyde? Yeah, that carbon, that carbon right there, because guess what? Again, oxygen, highly electronegative. It's going to pull electron density away from that carbonyl carbon, and that makes it a good electrophile, which means it's susceptible to nucleophilic attack. So alcohols, what we're going to see here, are going, in the right conditions, are going to attack that electrophile, right? And what we've done in this case, I've bound my alcohol to my carbon. I've made a brand new bond right here in blue between oxygen and carbon. And now I have, actually, let me ask you guys, what kind of a functional group have I just made? Ooh, I'm glad I asked. This is a hemiacetal. And since we had a little bit of trouble with this, let me give you guys the mnemonic that I've always used to remember this. What does the prefix hemi mean? Half. Why might the prefix hemi be particularly appropriate for this particular functional group? Split the double bond, that's a good idea, yeah. Half the substituents have oxygens, sure. Yeah. It's sort of half alcohol and half ether. Yeah. Look at this. I have two bonds. I have two bonds to oxygen. One of those bonds is to a hydroxyl group. One of those bonds is to an ether group. And by the way, this reaction, if you're looking at this and saying, this looks pretty obscure, Ty, I got news for you. This is actually extremely common in biochemistry. Where do we see this hemiacetal formation in biochemistry? Yeah, right? When we deal with the ring structure of carbohydrates, they go through a self-attack mechanism, giving them a hemiacetal ring structure. Right? Again, the way to remember this, hemiacetal, we have two bonds to oxygen. Half of them are going to be OH bonds, half of them are going to be OR bonds. Now take a look at this, gang. If I attack this with another alcohol, I get a full-on acetal. Let me ask you, how can you recognize the difference between a hemiacetal, a half acetal, and a full-blown, unqualified acetal? Right. No OH. I have two bonds to oxygen. Both of them are going to be two ether groups, two OR groups. Finally, notice two bonds to oxygen in the acetal, two bonds to oxygen in the hemiacetal. How many bonds to oxygen in the original aldehyde? Aha, still two bonds to oxygen in the original aldehyde. So what we're going to see here, gang, is that hemiacetals and acetals are still quite reactive in the same way that an aldehyde is, because they still have the same number of bonds to oxygen. However, the aldehyde is going to be the most reactive out of all of these. And think about what about the shape of an aldehyde would make it more reactive than a hemiacetal or an acetal? Yeah. There's the same bonds to oxygen in each, but the aldehyde is flat. This is the sense that we mean alcohols can be used as protecting groups. If I want to ensure that my aldehyde group doesn't get reacted in a reaction, what I can do is I can convert it into an acetal, which is going to be less reactive due to steric hindrance. And then after I've gone through my series of biochemical reactions, I can just turn it back from an acetal into an aldehyde. Now, what chemists have done is they've come up with a very specific way of doing this. The specific way of doing this we will see in just a second here. But let me ask you guys a related question. If I started with a ketone, which also is trigonal planar, also has a carbonyl carbon, and also is susceptible to attack via a nucleophile, I did these things, what would you predict I got? I did the exact same reaction starting with a ketone. I know it says it right there on screen, but let's reinforce that. Yeah, it'd get the same series of reactions resulting first in a hemiketal with half my bonds to OR, half my bonds to OH. A second round would bring me all the way to the ketal status. Cool. Now, what we've just seen here is that we can convert ketones or aldehydes into ketals or hemiacetals. And the most convenient way to do that is to use this diol shown here on screen. Because what we're able to do with this diol is the same mechanism where we're going to have nucleophilic attack on my aldehyde, forming a hemiacetal. But notice I already have my second quantity of alcohol ready, so that I get a second nucleophilic attack on that same carbonyl carbon, and that gives me my acetal functional group with very little muss and fuss, right? It's a one-step, in the lab, it's a one-step reaction. You mix these two together over heat, and that's going to drive over to that stabilized product. Finally, when I want to reverse this, I just put it in acidic conditions, and that pops off that protecting group, restoring my original aldehyde. And it actually can't attack this guy because he's so heavily oxidized. Cool. So we've got a couple more questions here. Right? And again, you can attack these questions for homework. For us, we're going to dive into our third learning goal of the day, now looking at basically the same set of ideas, but for aldehydes and ketones. Again, now last step sort of bridges us into aldehydes and ketones. Let's take a look at some of the properties of these guys. And again, we see some various reactions going on here. I'm starting with an aldehyde. What has happened to my aldehyde over here? What kind of a reaction is this? In the right track, Hannah, but I'm gaining more bonds to oxygen, right? Yeah, oxidation. And in fact, yeah, going to the left here, starting with my aldehyde, going to the left. How could I, this is good old-fashioned bleach, by the way. How could I recognize that as an oxidizing agent, ladies and gentlemen? It's got oxygen. Hannah, yeah, it does some oxidizing. It's got oxygen, sure. Yeah. So we can, for example, form an ester, and this is tying into a lot of stuff we already know, some trends we've already seen. How about going this way? What I've done is, oh my gosh, I have reduced the number of bonds to oxygen. What should we call this reaction, ladies and gentlemen? Reduction. Now, oftentimes, and again, I want to be clear, when we're doing redox in OChem, we are still transferring electrons in the traditionally defined way. This is just a great trick to recognize it at a glance. In organic chemistry, it also happens to be where these names come from in the first place. But let me ask you guys some follow-up questions. Usually when we reduce the number of bonds to oxygen, usually what do we make more bonds to along the way? Usually replacing bonds to oxygen with bonds to hydrogen. And what kind of a mnemonic could we use to remember that sodium borohydride is a great reducing reagent? Got lots of hydrides on it. Yeah, it's right there in the name. Sodium borohydride, right? So you will often see this schema on test day. Again, your organic chemistry teacher probably wouldn't be happy with you using these mnemonics. They're based in science. They're just pretty loose. But hey, it's the MCAT, not organic chemistry lab. Now, as for nomenclature of aldehydes and ketones, let's bring up some of the basics here. What suffix do I use for aldehydes? Al. Yeah. So if we're looking at this, maybe we can play the same game. What root would we be looking for the right answer to have? What we'd be looking for the suffix Al, the root but. Yeah. And what carbon is my chlorine on? 3. Yeah. So we'd be looking for like a 3, a but, and an al. You're going to get this question right on test day, right? Don't write that out for scratch. Find the right answer amongst the 4. Let's keep going here, right? Now, this is a weird situation. What I have here is a ring, cyclohexane, and I know many students, their first response is, let's call this cyclohexanal. The problem with that is that cyclohexane has 6 carbons. The root is Al. That implies one of my 6 carbons should be an aldehyde, and I can't have an aldehyde part of the ring. Here we have a separate carbon holding the aldehyde. So we need to add that to our name. And this is a weird little trick that comes up with cyclic carbons. But we call this cyclohexane carbaldehyde. Again, the carbaldehyde part is to indicate that there is an entirely extra carbon, a 7th carbon, holding that aldehyde group, right? Again, if you know this trick, you're going to spot it on test day, right? Continuing right along here, this looks very similar to example number 1, but what's different with this example, ladies and gentlemen? It's a ketone, yeah. So what root do we use, or what suffix, rather, do we use for ketones? Own. And be careful here, what would be the root that we would use for this particular ketone? Right. Yeah, we had to add a carbon to get it to be a ketone. In this case, that makes it a pentanone. Beauty. Yeah, notice we designated the location of the highest priority functional group with the lowest number. We still had the 4-chloro there as well. Right on. Now, this next question is very interesting here. What is the higher priority functional group here? I've got a ketone and an aldehyde. Beauty. Okay, yeah, we're a little split. I was expecting that. That's why this question exists, right? The answer is aldehyde. And the reason why is that, remember, the higher priority functional group is the most oxidized carbon. Now, we know that carbon atoms themselves are somewhat electron donating. So what we're going to see is that my ketone group has electrons being donated by both of these carbons, whereas my aldehyde group has electrons being donated by only one carbon. Less electron donation means more oxidation state, means higher priority. So the rule here is aldehydes get a higher priority. The suffix of this guy is going to be -al. That's the explanation why. If you don't want to learn that or memorize it, it's not going to hurt you on the MCAT. But if you ever wondered why aldehydes are higher priority, that is why. They have less donation from flanking carbons. The other question that this brings up is, okay, so we know the suffix here, but how do I treat ketone groups when they're not the highest priority functional group? Great. Yeah, so the addition of this one was a huge help to us. Again, we only have to recognize these trends, but we do still have to recognize these trends. Higher priority functional group, aldehyde. Ketone, not as high priority, so we call it oxo, 3-oxobutanal. That leaves us with this burly beast of a nasty monster. You guys tell me, what is one feature you're going to be looking for in the actual name on test day? I'm going to be looking for a cyclo. Yeah. Cyclo. I'm going to be looking for something to do with the aldehyde. But remember, gang, when I have aldehydes stuck onto a ring, how do we treat that special situation? We call it a carbaldehyde and an oxo. Yeah, again, the right answer here is going to have all of those features. It's got the oxo, it's got the cyclo, and it's got the carbaldehyde. That's going to be the correct name there. Cool. And let's take a look next at oxidations and reductions involving these bad boys, right? You're going to see a lot of the same trends repeating themselves overall. First off, potassium permanganate and Chris, the TAs are going to get your answer to that question. Potassium, I think it is also oxo. You have to use the context of the molecule to find out that the oxo is on the end of the molecule. Anyway, we're looking at aldehydes being oxidized, and we said, wait a minute, sometimes we want to oxidize all the way to the end. We do that using potassium permanganate, a very strong oxidant, which is going to add a extra bond to oxygen at the end of the molecule. There we have an exact repeat of something that we've talked about before. As well, these guys can be reduced via hydride donors. And again, this is an exact repeat of what we've talked about before. In fact, you guys help me out. We haven't seen lithium aluminum hydride before, but you guys can probably tell me, how do we recognize at a glance that lithium aluminum hydride is a super great reducing reagent? It's almost boring by now, isn't it? Right, exactly. Lots and lots of hydride anions. Beautiful, right? That's going to be reduction. And we see reduction reflected in the fact that we're reducing bonds to oxygen, gaining bonds to hydrogens instead. Great. Cool. Now, we're going to talk next about the reactivity of these molecules. We already did talk about this concept already, so we're going to jump past this part and get to some applications. But the physical properties they're going to be determined by the polarity of the carbonyl bond here. So first off, if we want to think about this is acetone. Acetone is super famous from your everyday lives. Where do you find acetone in your everyday lives? A nail polish remover. Now, ladies and gentlemen, if you spilled a nail polish remover, how long does it take for that stuff to evaporate? Yeah, like 2 seconds. It's just gone, right? What does that tell you about the intermolecular forces of aldehydes compared to ketones here, compared to, for example, water? Yeah, not as strong. In fact, what kind of intermolecular force are we looking at here specifically? Yeah, these are going to be actually dipole-dipole interactions, which are a type of van der Waals, right? So you can again appeal to basic ideas about electronegativity and dipoles in order to determine relatively advanced properties of these molecules. This guy overall is going to have a partial positive end, a partial negative end, and that's going to give him a great ability to have modest intermolecular forces, certainly stronger than propane, certainly less strong than anybody who could H bond. Nice. Dipole-dipole intermolecular forces. Partial positive end, we talked about that being a good electrophile. What we're going to see is that these guys are actually very, very reactive, and that aldehydes overall are better electrophiles than ketones. It says they're easier to attack. Let me ask you, why would an aldehyde be easier to attack than a ketone? Yeah, there's less steric hindrance. There's only one R group. Now, if we wanted to take that to the logical conclusion, both of these guys are certainly going to be a lot easier to attack than anybody who was SN3. Why? Almost anybody who was SN3. Think about how many different functional groups am I bound to if I'm SN3? What am I saying SN3? SP3. Jeez, no wonder you guys were not answering my question. Yeah, if I'm sp3 hybrid, I'm going to be bound to 3 different functional groups. And so, as a general rule, both aldehydes and ketones are quite reactive. They're good electrophiles, they're planar, so they're very easy to attack. It's just that aldehydes are a bit easier to attack than ketones overall. So if we take a look at a molecule that again has both ketone and aldehyde, the aldehyde is going to be the one that is more likely to be attacked because it has less steric hindrance overall. Nice, nice work here. Now again, we've got some questions associated with this topic, and these are going to be assigned for homework. We've got 2 more learning goals to go, so we're almost to the end of this lesson. This next one is the last one where we're really going to introduce anything new, and then our last learning goal is going to be all applications of things that we've just seen. So let's take a look at the acidity of alpha hydrogens, right? The alpha carbon is the one that's adjacent to a ketone. And what we're looking at is the protons that are associated with that. Now my question, we know that normally protons bound to carbons are not going to come off. They're so weakly acidic as to be just not acidic, right? The question for you guys is why in this special case would those protons be somewhat more acidic, relatively acidic, pKa maybe even around 18 to 20? Yeah, you guys remember our acidity trend from the beginning of this lesson with alcohols? We said that where there are electronegative groups, they're going to pull electron density away, and that's going to increase the acidity of this compound. Here we have the exact same idea in a brand new light. we talk about the acidity of alpha hydrogens, really we're talking about the inductive effect all over again. Now I want to point out there's a little typo here on slide. We're going to pop off a positive proton. What charge is that going to leave behind? And again, think independently here. If I pop off a positive proton, yeah, it's going to leave behind a negative charge. This should have said to form a carbanion. To form a carbanion. There we go. We're popping off one of these protons. That leaves behind a negative charge, aka a carbanion. Right. Now, if we think about reactivity of these, we said this guy right here, this carbonyl carbon, very susceptible to nucleophilic attack because he's a great electrophile. What about this guy right here, this newly formed carbanion? What kind of a reactant is this guy going to be? Negatively charged. He's got excess electrons. Right. What we've just done is we've made a very strong nucleophile. This is why aldehydes and ketones are such a heavily tested topic in organic chemistry and biochemistry. It's because we've got a great electrophile over here and a great nucleophile at the alpha carbon position, at least in the right circumstances, right? So furthermore, this guy can be resonance stabilized. So not only does he have the inductive effect helping him, but as we saw earlier, we can push electron density up onto the oxygen so that the electron density is actually sort of smeared around that whole region. Nice. Now, one more question for you guys before we move on past this topic. This is something that we'll see in just a minute as well. But this anion that's been formed is called an enolate anion. And there's a good reason for that, right? When we see the root word En, what does that indicate about the carbon backbone of my molecule? It's got a double bond in it, right? And again, we're seeing ideas repeat themselves in a brand new context. We formed this new double bond. That's why we call this an enolate anion. The ATE suffix almost always is associated with a anion of some kind of variety, and so that's where that name comes from. We see this reflected in a very famous reaction, keto-enol tautomerization. Now again, when we look at an enol, which is the molecule on the left, let's think ene because of double bond. Why the suffix OL? Yeah, it's got that alcohol group, that hydroxyl group, right? Versus a ketone. The idea of tautomerization is that we can flip from one of these molecules to the other. But guess what? We've already learned the entire mechanism of this situation, right? What we're going to see is that a proton deprotonates, leaving behind a negative charge on my alpha carbon. Electron density is pushed into this carbon-carbon bond, forming a double bond. We push the remaining electron density up onto oxygen, so it has a negative charge, and then we protonate that, giving us the OH. So again, we're seeing a lot of overlap of these very many ideas. Now, when it comes to forming enols, there might be a variety of enols present. That is, I could form the enol with the double bond to the right, or I could form the enol with the double bond to the left. My question is, which of these is going to be more stable based on what you guys know about organic chemistry? The one on the left is going to be stable. So over the long term, especially if we can flip back and forth between these, we're going to expect the inner one, or the one on the left, to be the one that's formed in higher abundance. However, what we're going to see is that the one on the right is going to form a lot faster. Why would you guys think that is? Why would the one on the right form more rapidly? There's less steric hindrance. Beautiful, yeah. So what we're going to see is that these two possibilities will both be expressed. The least hindered one forms more rapidly. We call that enolate anion the kinetic product. However, the more substituted one forms slower. It's called the thermodynamic product. However, it's going to be favored over time because it is, in fact, more stable overall. Nice, nice work, gang. Again, hopefully you're seeing that a lot of these ideas repeat themselves. Now, associated with this learning goal, we have two more questions. This last one about testosterone, so you can even see the bridge into overall biochemistry, biology, and your body. Doctors have to know this stuff because they work with these kinds of biochemical compounds. But let's look with our last 5 minutes at our fifth learning goal. We're going to look at nucleophilic addition reactions. And Anna, yeah, there's going to be a recap with answers to all these questions that have been assigned for mastering nucleophilic addition reactions. What we're going to do here is what most students of organic chemistry dread. That is, we're going to look at about 5 different mechanisms. But the reason why we're going to be able to do this in just 5 minutes is that all of these are going to boil down to the same fundamental set of steps. Nucleophile attacks electrophile and replaces some of those bonds. Nucleophilic addition to a carbonyl is the reaction that we're looking at here. So let's look at these molecules, starting with, who here is my nucleophile, gang? Who here is going to be my nucleophile? Water. Yeah, water is going to be my nucleophile. Where's my electrophile? Carbonyl carbon. Yeah, that ketone. Exactly. So what happens? Oh, well, nucleophile attacks electrophile, pushes electron density up onto the oxygen. Right? Now we have this intermediate where things are a little wonky, but through a little bit of adjusting of the protons, which makes total sense, we end up with our final product. I have 2 alcohols bound to the same carbon, gang. What do we call this? 2 alcohol groups, same carbon. A diol, and when they're bound to the same carbon, we give it a special name. Geminal diol. Geminal from Gemini, the twins. Now, the really cool thing about this, gang, is what have we done today? We've looked at a situation where we attacked a ketone and got a geminal diol. What if I had used an alcohol instead and gotten an OR group here and ended up with 1 OH group and 1 OR group? What would we have then? Close. Remember, again, we started with a ketone here, so not a hemiacetal, but a hemiketal. This means you guys today learned the mechanism to make geminal diols, hemiacetals, acetals, hemiketals, and ketals, and guess what? They actually ended up being the exact same mechanism every single time. They were all examples of nucleophilic attack on a carbonyl carbon. In fact, that's exactly what we're going to see here. We started with an alcohol. At the end of the day, that gives us a hemiacetal. Here again, the steps all make a lot of sense. We have our hemiacetal. We take a second iteration of the alcohol and attack again, and that gives us a full-blown acetal. Here we have 2 OR groups. I skipped the mechanisms here, gang, because of the point I just made. They're actually exactly the same mechanisms that we just saw. Nucleophilic attack on a carbonyl carbon, right? Same thing with ketals. If I start out with an alcohol group and a ketone, we're going to attack it to form a hemiketal. There's our hemiketal that we formed. If I bring in a second iteration of the alcohol, I have an excess amount of alcohol, why then I'll get a full-on ketone. And again, I'm skipping these because they're the exact same mechanism that we've learned today, gang. Now, one more mechanism, and again, we'll see that this is a similar reaction to what we've been seeing over and over again today. We want to make an imine. My question for you all is, what is an imine? At the end of the day, what is an imine? Yeah, it's like a carbonyl, only we've made 2 bonds to nitrogen instead of 2 bonds to oxygen. But what do you guys think is going to be the first step in this reaction, given my reactants that are shown on screen? nucleophile is going to attack the electrophile. Yeah, we will, exactly. We're going to have nucleophile attacking the electrophile. We formed a brand new bond. We play that proton shuffling game as follows, right? And then an interesting thing happens. We're going to see that my oxygen group, under the right conditions, my hydroxyl group can be protonated. Now we know that OH is a terrible leaving group. What about OH2+? Yeah, it's a great leaving group. It's right. What we've done is we've made an excellent leaving group. So under the right conditions, what we're going to see is a second round of attack, popping off that hydroxyl group and forming an imine. Again, so many different reactions, all basically following the same overall schema, right? We're going to end here. You guys have a few questions to work on for homework, but you see that a lot of this was fundamental principles. And if you come back an hour from now for our first OCHEM reaction, we're going to be doing even more of this. I want to say thank you guys for now. Stay tuned for Nzinga, and I might see you later on this evening. See you guys. Thanks a ton. Bye, everybody.